ever launched a catapult.
Yeah.
Or maybe tracked a stock price. Or even just, marveled at the curve of a suspension bridge.
Believe it or not, you've encountered the power of polynomials.
That's right.
They might sound a little intimidating at first, but trust me.
Yeah.
They're just a fancy way of describing relationships that we see all around us.
Absolutely. And today we're taking you on a deep dive into the world of polynomials using, you provided it, this Chapter 2, Polynomials excerpt
Yay.
from that math textbook. But don't worry, we're ditching the dry lectures here. Think of us as your guides to unravel the mysteries and reveal the magic behind these algebraic expressions.
Absolutely. So let's start with the basics, okay? What exactly is a polynomial? I mean, the textbook defines it as an algebraic expression with constants, variables, and exponents.
Yeah. It's kind of like building with Legos.
Yeah.
You've got your basic bricks, right? Those are your constants and variables. And then you have exponents. And those tell you how many times to multiply a variable by itself. But, and this is important, there's a catch. The exponents on those variables, they have to be whole numbers.
Okay.
That's one of the key things that makes a polynomial.
So no fractions or decimals allowed when it comes to those exponents, huh?
Nope.
Our textbook gives us examples like 2x that fits the bill, or x sacc plus 2x, also a polynomial, but something like x plus 2x with that fraction in the exponent, well, that wouldn't make the cut. Why? All the rules. What difference does a whole number exponent actually make?
Well, it's all about building a solid foundation for more complex math later on. Polynomials are kind of like the bedrock. They're the bedrock for understanding how things change and relate to each other.
Okay.
Think of them as the basic building blocks for understanding functions.
Okay, so functions kind of like you put something in, something happens to it, and then you get something out.
Yeah. You can think of a function like a machine, right? It takes an input, does something to it based on a set of rules, and then spits out an output.
Right.
Polynomials help us describe those rules.
Okay, so those whole number exponents, those are a pretty big deal. They're giving us this framework to describe and predict how things behave. Now, the textbook, it then gets into different types of polynomials. Monomials, binomials, trinomials. It's like they're speaking a whole other language.
Well, think of it like a family reunion, right?
Okay.
Each polynomial has a different family name based on how many terms they have.
Okay.
A monomial that's like that independent cousin who shows up solo. Just one term, like 2x.
Right.
Then you've got your binomials, the ones with two terms, always up for a good debate, like x plus 2x.
Yeah.
And finally, the trinomials, 3 terms, always adding their 2 cents to the conversation.
And our textbook gives us a whole bunch of examples to keep those family names straight. But it doesn't stop there, does it? They also introduce us to the idea of a polynomial's degree.
Right. The degree is just a fancy way of saying the highest exponent in the polynomial. It's like a polynomial's ID card.
Okay.
It tells you a lot about its personality.
Oh, interesting.
A linear polynomial that's 1 with a degree of 1. It's as straightforward as it gets, always representing a straight line on a graph. Then you have your quadratics with a degree of 2, known for their dramatic curves, like the arc of a basketball being thrown towards the hoop.
So we're talking about using a linear equation for a simple relationship, like figuring out how many miles you can drive on a tank of gas. And then a quadratic for something affected by gravity, like plotting the path of that basketball.
Exactly. You're catching on. But here's where it gets even more intriguing. Remember how we were talking about polynomials being like functions, those mathematical machines? Well, sometimes we want to know what makes those machines churn out a very specific output 0.
Ah, yes. The zeros of a polynomial. Sounds a little mysterious, doesn't it? Like we're trying to find the polynomial's secret code.
Kinda. It means figuring out which values you can plug in for x to make that whole expression equal to 0.
So if our polynomial is, say, x ln of 4, then finding the zeros would be like solving the equation x sans of 4 equals 0.
You got it. And those zeros, they're not just random numbers, right? They actually give us some valuable clues about the polynomial's graph. Imagine you're trying to plot the path of, a rocket launch using a polynomial.
Okay, I'm picturing it. A sleek rocket shooting upwards, its path arsing gracefully across the graph.
Now, those zeros, they tell you exactly where that rocket's path would intersect the ground. They're the points where the rocket's at ground level.
Wow, I never realized how much information you can get from just looking at a polynomial zeros. It's like having a secret decoder ring for these mathematical expressions. But our textbook, it doesn't stop there, does it? It throws a couple pretty hefty theorems at us, the remainder theorem and the factor theorem. I have to admit, those sounded a bit intimidating at first.
They sound fancy? but they're incredibly useful tools. Imagine you're dividing a giant pizza, that's your polynomial, into equal slices. The factor theorem helps you figure out if a certain slice size, that's your factor, will divide that pizza perfectly, with no leftovers.
No leftovers, that's the dream. But how does the remainder theorem fit into this?
Well, the remainder theorem is like your pizza slicing guide. It lets you quickly figure out how much pizza you'd have left over, that's the remainder if you divide it a certain way, without actually having to go through that whole slicing process.
So it's a shortcut for division. Sign me up. But how does knowing the remainder help us figure out if something is a factor? That's where the factor theorem comes in, right?
Exactly. The factor theorem takes that shortcut one step further. It says that if that remainder is 0, after you've used the remainder theorem, then, well, you found a perfect slice size, a factor that divides cleanly into your polynomial pizza.
So we use the remainder theorem to see if a potential factor divides evenly, no remainder, and then boom, we've got ourselves a factor. It's a two-step process, but way quicker than trying to just divide a complicated polynomial and hoping for the best. Speaking of making things easier, the textbook then jumps into factoring itself. And factoring is all about breaking down a big, complex expression into smaller, more manageable pieces, right?
You got it. It's like taking apart a complex Lego creation. You're trying to figure out the individual bricks that were used to build it. And just like with Legos, there are a couple of different ways to approach factoring. The textbook focuses on two main methods, splitting the middle term and using, well, we've heard of this one before, the factor theorem.
So our trusty factor theorem is back again, this time as a tool for actually doing the factoring.
Precisely. It's all connected. Each method has its strengths. Splitting the middle term, that's great for simpler quadratic expressions, the ones with a degree of 2, like finding those missing pieces of a simple puzzle.
And when we're dealing with those more complicated higher degree polynomials, that's when we bring out the big guns, the factor theorem.
You got it. That's when the factor theorem really shines. It helps us break down those complex polynomials into their core factors, making them much easier to work with.
It's like we've unlocked this whole new level of understanding with these factoring techniques. It reminds me of, those logic puzzles where everything seems jumbled up at first. But then once you find the right approach, boom, it all just clicks into place.
Exactly. And the best part is, once you've factored a polynomial, well, it opens up a whole world of possibilities for solving equations, understanding these complex relationships.
Yeah, like we've distilled those complex expressions down to their essence.
And speaking of making things simpler, the textbook, well, it saves the best for last, doesn't it? Algebraic identities. I'll be honest, when I first saw those, my eyes glazed over a bit. They looked like a whole lot of variables and symbols. I know what you mean, but trust me, these identities, they're like mathematical cheat codes.
Okay.
They're pre-derived formulas, and they can save you a ton of time and effort when you're trying to simplify expressions. It's like having a secret shortcut for those challenging algebra problems.
Okay, shortcuts, always a good thing. You've convinced me. So what are some of these magical identities, and how can they actually help us in the real world?
Well, the textbook lists several key identities. Like you have x plus y, x plus 2 by xi plus y, or x, y equals xy plus 3x at y plus 3 by y. Now, I know those might look a bit intimidating at first glance,
Yeah.
but the key is you don't need to memorize them. Just understand how they work and when to use them.
And the textbook does a great job of illustrating that with some practical examples. I was particularly impressed by the one where they used an identity to calculate 104 cubed without a calculator. It seemed like magic.
It's not magic, it's math.
Yeah.
But I see what you mean. These identities, they can make those seemingly impossible calculations, well, incredibly simple and elegant. They're really a testament to the power of recognizing patterns and finding those shortcuts in math.
It really is amazing how everything we've learned today, from those basic definitions to these powerful identities, it all connects together, doesn't it? To paint this richer picture of what polynomials are and why they matter.
Exactly. We started by, we demystified polynomials. We realized they're simply expressions built with those constants, variables, and those all-important whole number exponents.
Right.
We explored different types, from those simple monomials to the more complex binomials and trinomials. We even discovered how a polynomial's degree, well, that can give us clues about its behavior.
Yeah, and then we ventured into the world of zeros, learned how they can reveal some pretty crucial information about a polynomial's graph, and how those seemingly simple values, well, that tie into that powerful factor theorem, helping us break down polynomials into their core components.
And who could forget those mathematical cheat codes, those algebraic identities, always there, ready to simplify our calculations and make us feel like algebraic masterminds.
Polynomials, as we've discovered today, they're much more than just textbook equations. They're the building blocks for understanding relationships, describing change, and modeling all sorts of real-world phenomena, from the trajectory of a rocket to the curve of a bridge.
This deep dive, it was really just the beginning. There's a whole universe of knowledge waiting to be explored in the fascinating world of polynomials.
So we encourage you to take what you've learned today and keep exploring. What other real-world applications of polynomials can you find out there? What other mathematical mysteries are you curious about? Remember, there's always more to discover. And the journey, well, that's half the fun.